If probability is at the heart of quantum mechanics, what does that actually mean? Well, the fundamental source of probability in quantum mechanics is the wave function psi. Psi tells you everything that you can in principle know about the state of the system, but it doesn't tell you everything with perfect precision. How that actually gives rise to probability distributions in observable quantities like position or energy or momentum is something that we'll talk more about later, but from the most basic perspective, psi can be thought of as related to a probability distribution. But let's take a step back and talk about probabilistic measurements in general first. If I have some space, let's say it's position space. Say this is the floor of a lab, and I have a ball that is somewhere on the floor. I can measure the position of that ball. Maybe I measure the ball to be there on the floor. If I prepare the experiment in exactly the same way, attempting to put the ball in the same position on the floor and measure the position of the ball again, I won't always get the same answer because of perhaps some imprecision in my measurements or some imprecision in how I'm reproducing the system. So I might make a second measurement there, or a third measurement there. If I repeat this experiment many times, I'll get a variety of measurements at a variety of locations. And maybe they cluster in certain regions, or maybe they're very unlikely in other regions. But this distribution of measurements, we can describe that mathematically with a probability distribution. A probability distribution, for instance, I could plot P of x here, and P of x tells you roughly how many, or how likely you are to make a measurement. So I would expect P of x as a function to be larger here, where there's a lot of measurements, and 0 here where there's no measurements, and relatively small here where there's few measurements. So P of x might look something like this. So the height of P of x here tells us how likely we are to make a measurement in a given location. This concept of a probability distribution is intimately related to the wave function. So the most simple way that you can think of probability in quantum mechanics is to think of the wave function psi of x. Now psi of x, you know, is a complex function, and a complex number can never really be observable. What would it mean, for example, to measure a position of, say, 2 plus 3i meters? This isn't something that's going to occur in the physical universe. But the fundamental interpretation of quantum mechanics that this book in particular, that most physicists think of, is the interpretation that psi, in the context of a probability distribution, the absolute magnitude of psi squared is related to the probability of finding the particle described by psi. So if the squared magnitude of psi is large at a particular location, that means it is likely that the particle will be found at that location. Now the squared magnitude here means that we have to take the squared magnitude of psi. We can't just take psi itself. So for instance, in the context of the plot that I just made on the last page, if this is x and our y-axis here is psi, psi has real and imaginary parts. So the real part of psi might look something like this, and the imaginary part might look something like this. And the squared magnitude would look something like, well, what you can imagine the squared magnitude of that function looking like. And you can think of the squared magnitude of psi as the probability distribution. Let me move this up a little bit, give myself some more space. The squared magnitude of psi then can be thought of as a probability distribution in the likelihood of finding the particle at a particular location, like I said. Now, what does that mean mathematically? Mathematically, suppose you had two positions, A and B, and you wanted to know what the probability of finding the particle between A and B was. Given a probability distribution, you can find that by integrating the probability distribution. So the probability that the particle is between A and B is given by the integral from A to B of the squared absolute magnitude of psi dx. You can think of this as a definition, you can think of this as an interpretation, but fundamentally this is what the physical meaning of the wave function is. It is related to the probability distribution of position associated with this particular state of the system. Now, what does that actually mean? And that's a bit of a complicated question. It's very difficult to answer. Suppose I have a wave function, which I'm just going to write as the square, plot as the squared magnitude of psi now. Suppose it looks something like this. Now that means I'm perhaps likely to measure the position of the particle somewhere in the middle here. So suppose, wrong color. So suppose I do that. Suppose I measure the position of the particle here. So I've made a measurement now. Messy handwriting. I've made a measurement, and I've observed the particle to be here. What does that mean in the context of the wave function? Now, everything that I can possibly know about the particle has to be encapsulated in the wave function, so after the measurement, when I know the particle is here, you can think of the wave function as looking something like this. It's not going to be infinitely narrow because there might be some uncertainty. The width of this is related to the precision of the measurement. But the wave function before the measurement was broad, like this, and the wave function after the measurement is narrow. What actually happened here? What about the measurement caused this to happen? This is one of the deep issues in quantum mechanics that is quite difficult to interpret. So what do we make of this? Well, one thing that you could think, just intuitively, is that, well, this probability distribution wasn't really all the information that was there. Really, the particle was there. Let's say this is point C. One interpretation is that the particle really was at C all along. That means that this distribution reflects ignorance on our part as physicists, not fundamental uncertainty in the physical system. This turns out to not be true, and you can show mathematically and in experiments that this is not the case. The main interpretation that physicists use is to say that this wave function psi here, also shown here, collapses. Now that's a strange term, collapses. But it's hard to think of it any other way. Suppose you were concerned with the wave function's value here. Before the measurement, it's non-zero, whereas after the measurement, it's 0. So this decrease in the wave function out here is, it's reasonable to call that a collapse. What that wave function collapse means is subject to some debate, and there are other interpretations. One interpretation that I'll mention very briefly, but we won't really discuss very much, is the many worlds interpretation, and that's that when you make a measurement like this, the universe splits. So it's not that the wave function all of a sudden decreases here, it's that for us, in our tiny little chunk of the universe, the wave function is now this, and there's another universe somewhere else where the wave function is this, because the particle was observed to be here. Don't worry too much about that, but the interpretation issues in quantum mechanics are really fascinating once you start to get into them. You can think about this as the universe splitting into, splits. The universe, you can think about this as the universe splitting into many little sub-universes where the probability of where the particle is observed at a variety of locations. One location per universe, really. This question of how measurements take place is really fundamental, but Hopefully this explains a little bit of where probability comes from in quantum mechanics. The wave function itself can be thought of as a probability distribution for position measurements. And unfortunately, the measurement process is not something that's particularly easy to understand. But that's the fundamental origin of probability in quantum mechanics. To check your understanding, here is a simple question about probability distributions and how to interpret them. First, if I have some space, let's say it's position space. Say this is the floor of a lab, and I have a ball that is somewhere on the floor. I can measure the position of that ball. Maybe I measure the... If probability is at the heart of quantum mechanics, what does that actually mean? Well, the fundamental source of probability in quantum mechanics is the wave function psi. Psi tells you everything that you can in principle know about the state of the system, but it doesn't tell you everything with perfect precision. So I might make a second measurement there, or a third measurement there. If I repeat this experiment many times, I'll get a variety of measurements at a variety of locations. And maybe they cluster in certain regions, or maybe they're very unlikely in other regions. But this distribution, of how that actually gives rise to probability distributions in observable quantities like position or energy or momentum, is something that we'll talk more about later. But from the most basic perspective, psi can be thought of as related to a probability distribution. But let's take a step back and talk about probabilistic measurements in general, all to be there on the floor. If I prepare the experiment in exactly the same way, attempting to put the ball in the same position on the floor and measure the position of the ball again, I won't always get the same answer because of perhaps some imprecision in my measurements or some imprecision in how I'm reproducing the system.